All right, well, good afternoon, everyone. Thanks for coming along. Can I just confirm that the sound's working okay?
Yeah.
That's good, thank you. Okay, well, let's get started. All right, so first thing, I just had it pointed out to me this afternoon that there's a typo in the notes from last week. So where I was talking about dealing with consistency ratio problems just here, I talk about making a change that would fix the problem, but I put the wrong consistency ratio there. That should, I believe, be 0.06. So I'll make that change and that will be in future versions of the notes. But thanks to the person who pointed that out. And if you do come across typos, please let me know. I won't be offended. I really appreciate knowing about them. Okay. All right. Now we're going to do three things today. I hope we have time for them. So the first one is just a little bit of wrapping up on regression and correlation that I want to do. I did cover some of this in the tutorial last week, but I'll go over it again, and then that will be it on correlation for the time being. We will come back to it later when we start talking in more detail about causation, but this is just the sort of last few odds and ends. The main reason I'm talking about the stuff I'm talking about today is because it's useful to know when you are reading things like journal articles and trying to appraise them. Second thing I then want to do is explain to you what the the hierarchy means in analytical hierarchy process. So I've got a couple of examples, a sort of toy example, and then a serious real world case to take you through. And then if we have time at the end, we'll just start with a little example to introduce how statistical inference works. So we've seen a version of this scatter plot a few times now. So this is the Washington bike rental data. This is a scatter plot of the relationship between temperature, average daily temperature, which is the independent variable, and the number of bike rentals, which is the dependent variable. And this time I'm using a subset of the data I used before. So instead of the full year, I've got 365 days, I've got about 240 days that I've randomly selected, mainly so you can see what's going on a little bit more clearly. So what we did was you'll recall we've now talked about this. I think this is the third week. We fitted a regression line. So this is a linear, what we call a linear model. And what that means is the model in 2 dimensions at least is a straight line. And it's meant to help us predict predict the dependent variable if we know the independent variable. And it can be expressed as what we call a linear equation. So that is the equation there. So the number of rentals is predicted to be 3,187 plus 154 times the temperature in degrees Celsius. And it's not a bad model. So one of the ways we judge a model like this is we look at something called the adjusted R squared, and the adjusted R squared in this case is 0.51, and that's actually a pretty good value. And with a simple model like this, where you just have it's a linear model and you just have a dependent variable or an independent variable, and you're pretty confident that the relationship in the real world is approximately a linear model, in other words, a relationship in the real world is a straight line relationship, we can look at something called the Pearson correlation coefficient. And most people, when they talk about correlation, if they quote a number, that's the number they'll quote, is the Pearson correlation coefficient. But it is important to remember that that number is really only very meaningful if the real world relationship between the dependent and the independent variable is actually something like a straight line. Now, when we look at that, we can see it's not quite a straight line. It's a bit curved, and it's kind of straight in the middle between sort of about 10 and 20 degrees. It's fairly straight, you know, in that roughly in that region there to there. It's pretty much a straight line, but it starts to curve down as it gets very hot or when it gets very cold. And when you think about that, that makes some sense in terms of what most of us would know about wanting to do physical exercise at different temperatures. Once you start to get up around 30 degrees, it starts to become a hard work, particularly if you're riding a bike, you know, around the city on a working day. So that's fine. But these two numbers, these are, well, the R squared in particular is one of the numbers that we call an effect size with this kind of model. And when you're reading, you know, you're looking at journal articles, they will quote usually, not always, but they will often quote the adjusted R squared. And that's important to look for because that gives you an idea of how much the independent variable explains about the dependent variable. So if the R squared is very large, that tells you that the independent variable is a very good predictor of the dependent variable. If it's very small, not so much. The other thing that we look at in regression is this number here, the 154, which is multiplied by temperature by the independent variable. That's called a beta coefficient, and that gives us an idea of how much effect the temperature has on, in this case, the bike rentals. So what that number there is telling us is every time the temperature goes up 1 degree, it's predicted that the number of bike rentals will go up by 154. That's the meaning of that. So that's a different kind of effect size. So both of those are things that we typically will sort of quickly start looking for if we see that somebody's done a linear regression. So there are these kind of rules of thumb about what are weak and medium and strong correlation coefficients and adjusted R squared. And these exist for many types of statistical procedure and model. And a lot of them can be traced back to this guy, Jacob Cohen, who wrote a book on the subject, a number of articles, and kind of pushed the idea of paying attention to effect sizes. And but he was very clear when he was talking about these things. These are just rough guides. Don't get too hung up on them. But of course, what do academics do? They get totally hung up on them. So take them as rough guides. In the second half of the course, at some point, I'll show you some charts that I've prepared that will give you an idea of what these mean in practice. But for the correlation coefficient, 0.1 is a small effect, 0.3 is regarded as a medium effect, and 0.5 is a large effect. So that linear model there, that's actually, with its correlation coefficient of 0.71, that is squarely in the category of a strong correlation, even though when you look at it, you see it's not that great a predictor. You know, we've looked at this before in the class, but, you know, say for 20 degrees, if you sort of go up there, around that area, at the low area, you've got a point down here, 5,800 or something, and then higher up, roughly, you've got, you know, 8,500. That's a big range. So it's not a super precise predictor, even with its very large correlation coefficient. These correlation coefficients, remember these Pearson ones, and most types of correlation coefficient are designed so that they range from -1 to 1. and negative numbers mean a negative correlation. So that would be a line that was sloping downwards. And positive numbers mean a positive correlation, and 0 means no correlation. And then we have the effect sizes for the adjusted R squared, and they are sort of approximately the square root of the effect sizes for the correlation coefficient. So this one's got an adjusted R squared of 0.5. So that would be regarded as a very big R squared. But I've got to tell you, when I first started getting interested in this stuff, and this is years and years ago, I did a course for researchers on regression, and it was an interesting course because it was run for the whole university. So you had I think I was the only person there from business, but we had people from accounting, we had physicists and astronomers and biologists and geographers and all sorts of people from all sorts of disciplines. And what we learned was that different disciplines really have different standards. So from some disciplines, I won't mention any names, but they would regard effect sizes like this as ridiculously small, and other disciplines would regard them as huge. It depends a lot on the kind of data that you're working on, the kind of models, and so on. Okay, so the other thing to remember, and I'll keep mentioning this, it's important to remember, is the Pearson's correlation coefficient is working on the assumption that the data, the measurements, have been made of something that has a linear relationship in the real world. Okay, that's important to remember. If it's not a linear relationship, then you've got to discount the correlation coefficient. And we will come back to that idea later in the course, but it's just important to remember that, because what happens a lot is, people get a table in Excel or something with two variables, and it takes about 20 seconds to produce a correlation coefficient. And then they get very excited if it's bigger than 0.3. But it's not necessarily telling you anything very useful unless you have sound reasons to believe that the things that have been measured have a linear relationship. So you just need to be careful. All right, I want to turn now to something that has various names. The naming of things here is very confusing, so I'll try and make it as clear as I can. The headline term I've used here is nonlinear regression, but well, let's see how we go with this. This is the same data set, but what I've done here is I've fitted a non-linear model. So you can see the model, the red line there, it's curved. It's a section of a parabola. And I've done that by, what I've actually fitted is not a linear equation, but a quadratic equation, which is this one here. So you'll see that what makes this a quadratic equation is that it has T, temperature, and temperature squared in it. So, as I say, the term I've used is nonlinear regression. Various people give this various other names. Let me tell you how it's done. What you actually do is you do a linear regression in the normal way, except that you tell the linear regression algorithm, the computer, to take into account the temperature and the temperature squared. And the computer will do that. It will basically use the linear regression method of calculating a model, but it incorporates the squared value as well. And what you get out of that is an equation like this. Now, so what makes the terminology confusing is a lot of people will call that, it's very commonly called linear regression, simple linear regression, but with a transformed variable. And transform means you do something to it like square it. So in this case, it's squared. There's lots of other transformations. There's square roots, logarithms, various kinds of power transformations and things. There's a whole lot of them. And when we looked at the article in the tutorial last week, we saw that lots of the independent variables in that one had various kinds of transformations to them, mostly square roots and logarithms. So this is done quite a lot. It's sometimes used to straighten something that's bent, or sometimes to bend something that's straightened. But that's what I've done there. Now, the effect of this, we still get an adjusted R squared out of this. And you can see the adjusted R squared is quite a lot better. It's 0.62 now, so it's gone up from 0.51 to 0.62. So that's quite a bit stronger. But we don't now use Pearson's correlation coefficient. So one is we're not assuming, for two reasons. We're not assuming that there's a linear relationship in the real world. We've looked at the scatter plot and we think, okay, the scatter plot gives us reason to think it's a non-linear relation. It's a curved relationship. And secondly, that corresponds to, well, not just common sense. You can, if you do even, 10 minutes Googling around journal articles on temperature and exercise, you'll find that the relationship is known to be non-linear. It's pretty extensively studied. So we've got good reasons to think it's a non-linear relationship. The second thing is that we now don't have a linear equation. So we just forget about Pearson's correlation coefficient now, and we would just report the R squared. So that's one kind of deviation from the simple linear model. It's really quite a common one. You just need to keep an eye out for it. When you're looking at an article that does this, it's good to, and I pointed this out in the tutorial, it's good to look to see whether the authors actually justify doing this, provide some theoretical justification or some evidence as to why the transformation of the variable is justified. Sometimes they just do it because it gives them a better model, but that is, how can I put it? It can be a questionable practice. It's something you just need to watch out for. Now, the next, and thankfully the last one I'm going to talk about is multiple regression. So multiple regression is the one that you will come across most often in journal articles in some form. And there are lots and lots of variants of this. But the basic idea is that, the central idea is that you'll have a linear regression, but it'll be one where you have two independent variables or more. You can have lots of independent variables. So the one I'm going to show you is, again, our bike data. So we've got the daily rentals, the daily average temperature, and then this one, H, is the daily average temperature, daily humidity, sorry. And what we'll ask the computer to do is to come up with an intercept, A, it's just a number, and then two other numbers, a B1, a beta coefficient for temperature, and another beta coefficient for humidity. And it's still a linear equation, but as you'll see, when we look at it, it's in 3 dimensions, not 2 dimensions. So I feed this into the computer, it does its magic, and that's what it came up with. So it came up with an intercept of 4809 and a beta coefficient for the temperature of 159 and for the humidity of -29. So how do we interpret that? Well, the 4809, that's the prediction for bike rentals if the temperature was 0 and the humidity was 0. Now, a temperature of 0 in Washington is quite plausible. There are some days in the data set where it gets to 0 or a bit below 0. I'm not sure that a humidity of 0 is plausible. I can't quite imagine what that would be like. I'm sure there's no days in our data set that have humidity of 0. This is something you'll often find is you'll get a linear equation or an equation from your regression, but it doesn't necessarily make sense for some of the variables to be equal to 0. That's normal. So this intercept can be a sort of bit of a hypothetical thing. Most of the time, we don't pay much attention to that. We use it in the equation if we're doing predictions, but we're not so much interested in that. We're more interested in these coefficients. So what these coefficients, first thing it's telling us is that as the temperature goes up, on average, the rentals will go up by 159 per day. And it's also telling us as the humidity goes up, the rentals will go down on average by 29 a day. So it's telling us that the effective humidity is in the opposite direction to the effective temperature, and that the effect size for humidity is smaller than the effect size of temperature. It's 29 per day for humidity, 159 days per day for temperature. Okay. So this model, by adding in humidity, we've improved the model a bit. So the adjusted R squared has gone from 0.51 to 0.55. So it's a little bit better at predicting. But it's not as good as our beautiful curved model up here, which just uses temperature. And I'll just say I'm not going to do it. I perfectly could add in minus temperature squared there and run it again, and I have indeed done that, and it gives us a somewhat better model, but we'll forget about that. Now, the thing about when you've got two variables here, you don't get an equation for a line. What you get is an equation for a plane in three-dimensional space. So that's what it looks like. Now, a three-dimensional diagram like this, a lot of the time they're not terribly useful, but in exploratory data analysis, we do use them sometimes. When there's not much you can really kind of tell from looking at that, I don't think. You can sort of see a bit of curvature there. There are tools you can use which enable you to draw a 3D scatter plot and rotate it and turn it upside down and so on, and that can sometimes help you get a better idea of what's going on, but it's often no quicker than just running a bunch of regressions with different variables to see what sort of structure is there. So so that's what it looks like. So you have temperature here on the x-axis. Humidity is now on the I've got that on the z-axis, they usually call that, and then rentals is on the y-axis, the dependent variable. And the way we use that, I'll show you, but no one ever does this in practice. Let's say that point there, it's a bit hard to tell, but that was actually the hottest day in the data set. So what we do is we find the temperature, we find where the temperature intersects with the humidity for that particular day, somewhere there. And then we go up through our point, we hit the plane, and then we go across to the dependent variable axis, and we get our prediction, which was 8,000 and something. It wasn't terribly accurate. I think the real number was 5,600 or something, but that's how it works. But nobody, as I say, I'm certainly not going to give you an exam question where I give you a scatter plot like this and ask you to work out a prediction for something, but that's how it actually goes. Now, what happens when you get to 4 dimensions? Well, when you get to 4 dimensions, what you have is a 3-dimensional hyperplane in 4-dimensional space, which I can't even imagine, let alone draw. And people can, there are situations where people do regressions that have hundreds or sometimes even thousands of independent variables. It's a very scalable kind of technique. So the computer is actually working away and can be working away in hundreds or thousands of dimensions, but it will still produce a linear equation. There'll just be a whole lot of independent variables. Now, in the other direction, how low can you go with variables? Well, the lowest we've looked at so far is 2. Let's have a look at 1. So this is a 1-dimensional scatter plot, and this is our bike rentals. So we've only got one dimension there. We've got a y-axis. And that's the linear model, so the linear equation. So the linear equation is R equals 5595. So you can see there's no independent variable there. There's just an intercept. And we can draw the same chart. We can put the intercept on there. And this is a very simple model because the answer is always 5595. If you want to use this model to predict how many bike rentals there will be on a given day in 2012, the answer is always 5595 every day, because this doesn't do anything to take into account temperature or humidity or anything else. Now, this linear model has a very special name. Does anyone know what it is? Okay, this is the arithmetic mean. So that's what the mean is. So the mean is a one-dimensional linear model that predicts the values of which it is the mean. So it's basically the least inaccurate predictor of the values in a variable. So it's another way of thinking about what the mean is. It's very different to what the median is. The median is what's in the middle when you sort them and put them in a row. They are both statistics that are meant to give us an idea of where the center of the data set is, or the center of a variable, but they work in very different ways. And they have, apart from this kind of basic function of giving us a general idea of the center of a variable, they are used for the most part for very different purposes. Okay, so that's it for regression. And I want to move on to the last bit about the analytic hierarchy process. So the analytic hierarchy process, I think it was invented, I don't know the exact date, but somewhere around about 1970 by a fellow called Thomas Sati, who I think is still alive, and he was now a very famous management scientist, we used to call them, or operations researcher. And he was a lot of the work that management scientists and operations researchers do is around. Oops, sorry. Just before I go on, I've got a couple of questions there. Now, Sarah, I probably need to jump back to what your question was about which chart. On the 3187, was it? Oh, this one. Yes. So if we extend that line down, that should cross the y-axis at 3187. So that's always the case with a linear equation. The intercept is it's called the intercept because it's where the line intercepts the y-axis. Now Mako's question about R squared, but results are more reliable. I'd be cautious about using the word reliable in this context because it has a number of other quite specific meanings in statistics. But the way it's usually explained is the R squared tells you how much of the, let me clean the diagram up a bit. Okay. What the R squared actually tells you is how much of the variation in this direction is explained by the independent variable. So the way I tend to think of it is, how much information does the independent variable give me that would allow me to predict the dependent variable? So the bigger the R squared, the better it's going to be at predicting. Now, for the parabola example, so Sarah's asked us about whether we use R squared. Yeah, we do. So the actual, the method of working out what that line is this, it's essentially the same underlying algorithm or mathematical procedure as you use in any other, in any linear regression. And it produces an R squared, and you interpret it in exactly the same way. So the R squared for this one here, which I think was 0.71, that's telling me that the temperature gives me 71% of the information I need to know to predict the rentals. Or, as I said, the more conventional way of saying it is the temperature variable, the independent variable, explains 71% of the variance or the variation in the dependent variable, the rentals. That's the usual way of explaining it. Is that good? Okay. I'll get back to my friend Thomas. Okay. So what? So historically, management scientists, operations researchers, whatever you want to call them, they were mainly interested in things to do with manufacturing and logistics and that kind of thing. And they did certainly got involved in work on decision making, but others were working on decision making as well, economists and psychologists and so on. Okay, let's talk a bit more about R squared and Pearson. So Pearson only works when you've got two variables. So for the Pearson correlation coefficient, you have to have two quantitative variables. They have to be interval level or ratio level quantitative variables. And the relationship between the two variables has to be a linear one. To be able to interpret the Pearson correlation coefficient, the relationship between the two variables has to be approximately linear. They're the main requirements. Now, when you just have two variables, this is where it is perhaps a little confusing. When you just have two variables, the R squared happens to be the Pearson's correlation coefficient squared. Okay. So if you just have two quantitative variables which are in a linear relationship to each other, then the R squared will just be the Pearson correlation coefficient squared. But that relationship doesn't exist when you have more than two variables. So if you have a multiple regression, you have a minimum of three variables. You have a dependent variable and you have at least two independent variables. And there's no such thing as a Pearson correlation coefficient then. But regression will give you, ordinary linear regression, will give you an R squared value. And the R squared value does tell you something useful. It tells you how well that combination of independent variables does at predicting the dependent variable. So in the simple case we looked at, which was humidity and temperature, this had an R squared of 0.56. So what that's telling us is the combination of temperature and humidity together, those two variables, they explain about 56%, I think it was, or something like that, of the variation in the rentals. Or they give you about 56% of the information you need to predict the rentals. Does that help?
Yeah, so with the example of the adjusted R-square of 0.51 and the Pearson coefficient of 0.72, so 51% of the independent variable explains the dependent variable for the adjusted R-square. So with the Pearson coefficient for correlation coefficient for two quantitative variables, it's just basically saying whether it's a strong correlation or not.
Yeah.
Okay.
Yeah. So yeah, you can only use the Pearson one when you've got two quantitative variables, and you have to be very careful about the interpretation of them if it's not a linear relationship. Later in the course, I'm going to show you some examples where the Pearson one really is not the one to apply. But even this case here, it's what I would regard as good practice is if I were reporting this in an article, is I would probably show the scatter plot, or I would say, the Pearson correlation coefficient was whatever it was, I've forgotten already. What was it? 0.72, which is very strong. But I would point out that a better fit to that data is a quadratic model. There is some curvature there. Okay, my view is that I should have discovered that through exploratory data analysis, and B, I shouldn't hide that fact, because in this case it's very likely meaningful. Now, R squared basically has an upper threshold. It's a positive number between 0 and 1. I think occasionally, don't think I've ever seen it, but sometimes the algorithm might sometimes give you something that's a little bit slightly over 1, but basically it's 0 to 1. Okay. So let's get back now.